Welcome back to ECE 320A. In this video, I want to illustrate that you don't have to find complex numerical values for residues when you're working with these exponentially damped sines and cosines, and you can actually use real number arithmetic when trying to find the inverse Laplace transform. So let's look at that relative to a particular example and try to make that a little bit more intuitive. And then at the end of this video, we will talk about the equivalence of a sum of sine and cosine. They have to be at the same frequency, that being the same or equivalent to a cosine that might be that has a phase shift associated with it. So let's now look at this particular example of complex poles with real number arithmetic. And I hope by this point you're feeling very comfortable with the fact that in this factored form of the quantity s plus 2 squared plus 3 squared, that now is or has values of s that cause that to vanish, equaling minus 2 plus and minus j 3. Once we have those complex poles, we should immediately be able to start to think about what the structure of the time domain response looks like for a factor that has as a denominator an s plus 2 squared plus 3 squared. And in particular, f of t looks like an exponentially damped cosine. What's the exponential damping? So let's say we now are going to weight the cosine with a coefficient of a. What's the exponential piece? That's influenced by the real part of that complex pole, which is now going to say that we have an exponential damping of e to the minus 2t. Let's say this is now our cosine piece. What's the frequency? Well, that's the imaginary component of that complex pole. So that's now cosine of 3t. But we have a numerator that's not necessarily exclusively associated with a cosine transform or a sine transform. It could be some combination. So in general, the structure has to possess both a cosine without a phase shift at the frequency 3t and the sine. So the sine is then b e to the minus 2t sine of 3t, and all of those are for non-negative values of time. Or we could write this as some magnitude c scaling an exponential e to the minus 2t. That's the same in both the cosine and the sine. But now we could say, well, that a cosine plus b sine is equivalent to, or can be shown, which we will show at the end, that that's equal to this cosine of 3t plus theta for t greater than or equal to 0. And now this might be easier to sort of sketch mentally in your head. You now know that you have just a single waveform at a frequency of 3, a damped frequency of 3 radians per second. And now it's just with that phase shift, the t equals 0 point is shifted a little bit from having a pure cosine that maxes out right at t equal to 0. What we want to do in this first part is actually inverse Laplace transform this capital F of s in the form of this cosine and sine summation structure. So what we're wanting to do is find a and b using real numbers in our arithmetic. So we're asking the question, what are these coefficients, or what are their values? What are the values for a and b? Well, the way that we will do that is we will say f of s is now 5s plus 2 over s plus 2 squared plus 3 squared. And now we know that that's some linear combination of a cosine, but we know the structure of the Laplace transform of an exponentially damped cosine. It's s plus 2 over s plus 2 squared plus 3 squared. So this piece right here is the cosine piece. And we also know that it's some linear combination plus b times the sine. And the sine's Laplace transform, the denominator is the same, has the same exponential damping, that's the s plus 2 squared piece, and it's oscillating at the same frequency of 3 radians per second. Now we simply need to put the structure in the numerator associated with the cosine piece, so that this piece, now that I'm highlighting in blue, is associated with the sine piece, S-I-N-E. What we want to do now is find A and B, but we've done this really in one of our strategies for finding these residues or these partial fraction expansion coefficients. Look at what we have in that expression. And in particular, look at the denominators. The denominators already are the same. So we already have a common denominator, which means that in order for this left-hand side to be equal to the right-hand side, the numerators have to be the same. And the numerator simply says that 5s plus 2 is equal to as plus 2a plus 3b. And now we know how to make this happen. We just have a linear polynomial in s on the left equaling a linear polynomial in s on the right. The coefficients have to be the same for the same powers of s. If we now look at the coefficient that's weighting the s term, on the left we have 5, and on the right there's only one term that involves an s, and that's a. And now, even though we have two equations in two unknowns, or two unknowns, and we would anticipate two equations since we have a s to the 0 and s to the 1, these actually are somewhat decoupled in that the a coefficient is immediately found by equating the coefficients associated with s. If we look at the constants, on the left we have 2, and on the right we have 2a plus 3b, but we already know a, so that gives us 2 times 5 plus 3b, and we can now solve that for b. We have 2 minus 10, or minus 8, all divided by 3, and b is now minus 8/3. So that with these coefficients now found using real arithmetic or real number arithmetic, f of t now is a, which is 5, weighting the exponentially damped cosine piece, which is e to the minus 2t cosine of 3t minus 8/3 e to the minus 2t sine of 3t. And again, that's the one-sided Laplace transform, so this is valid. This formula starts at t equals 0 and marches on for all positive values of t, or this is true for non-negative values of t. Now, if you had gone through and used your calculator or found this using the k over the distinct pole at minus 2 plus j3 plus k star over the distinct pole factor associated with minus 2 minus j3, you would have ended up with a pure cosine expression, and here we have a sum of a cosine and a sine. Meaning you might be saying, but my answer was a cosine. Well, that's because you actually solved it using complex numbers. And using complex numbers, f of s would have been then 5s plus 2 over s plus 2 squared plus 3 squared, and that's now equal to k, let's say k1 over plus k1 star. And what's downstairs? Now it's critical that we get the right denominator underneath the correct k. K1 is not the conjugate, so K1 has to be associated with the pole located in the second quadrant. So we want to know what factor is underneath K1 and what factor is underneath K2. We know the poles are at -2 plus and minus J3. Well, we want underneath K1, we want the pole -2 plus J3. So if we now have S is equal to -2 plus J3 sitting underneath K1, then we can add the complex number to both sides, or we now have S plus 2 minus J3 equaling 0. So we now know that this polynomial underneath K1 for the distinct pole at -2 plus J3 is going to be S plus 2 minus J3, and underneath the conjugate of K1 is S plus 2 plus J3. Now we know that this one is in the second quadrant. And that is critical for the association with K1, the unconjugated form of that residue. Now to solve for K1, we multiply both sides through by that denominator factor, which is S plus 2 minus J3, and evaluate at the location that causes that factor to vanish, which is -2 plus J3. Or, now K1, the numerator was 5s plus 2, and we've now canceled this particular factor from our denominator, and so now in the denominator we're left with s plus 2 plus J3, and we want to evaluate that at s equal to -2 plus J3. And if we do that, complex arithmetic, we end up with 2.5 or 5/2 plus J 4/3. Or that's the rectangular form. We could put that in polar form by finding the magnitude of that complex number, which is 17/6, and it has an angle given by the inverse tangent of the imaginary part over the real part, or we now have 2.833 at an angle of 28.7 degrees, which, using that complex expression for the residue k sub 1, the time domain expression is 2 times the magnitude of K1, e to the minus, now where was our pole? It was at -2, so e to the -2, cosine, it had an imaginary component of 3, so our damped frequency of oscillation is 3 times time plus the angle of k, which we now know is 28.07 degrees. This is now the angle of k, and actually it was K1, and K1's magnitude was 2.833, so that if we wanted to double that, it would be 5.67. So now f of t is now 5.67 e to the minus 2t cosine of 3t plus 28.07 degrees for t greater than or equal to 0. What you may be wondering is, how is this, which is a cosine expression with a phase shift, how is that the same as this expression? And that's what we want to look at now. How can we convince ourselves that those two expressions are indeed the same f of t? They are equivalent. So let's now look at, and one of the key things to keep in mind is that the frequency on the sine and the cosine are the same. And that's the same as this damped frequency in the single cosine expression with a phase shift. So let's now look at how we can determine or verify that this single cosine with a phase shift, and now we're saying that k bar is some 2 magnitude of k, e to the minus alpha t cosine of beta t plus the angle of k, that's equal to some a e to the minus alpha t cosine of beta t. Note that that exponent and that exponent are the same as that exponent, and this frequency of beta, damped frequency, is the same in all of those terms. We want to now show that the left-hand side is equivalent to the right-hand side. Just to make it more confusing, no, I'm not really doing that, but I'm hoping that now you can see the connection between these. Capital R is now the k bar, the omega is the beta, and the sigma is alpha, and the theta is the angle of k. Let's start with this single exponentially damped cosine with a phase shift of theta and a magnitude of, or an amplitude of r. And this phase shift really is just saying that we have a time shift relative to when this particular cosine is a maximum. And you can see that if you simply look at the argument and factor out the omega. Now you have t plus theta over omega, and now you have an advance of theta over omega degrees. So if theta was negative, you would have this time delay of an amount, theta over omega. Here you have an advance because of the plus sign, if theta is positive, of theta over omega. Now, the first step in showing this equivalence is to just recall the trigonometric formula for the cosine of the sum of two angles. Here we're saying one angle is omega t, and the other angle is theta. We have a sum of those two, a plus sign in the argument of cosine. The trigonometric identity then says cosine of the first angle, omega t, times cosine of the second angle, theta, minus the sine of the first times the sine of the second, is equivalent to this sum of cosine omega t plus theta. We're keeping r e to the sigma t. Now what we're trying to do is show that that's going to give rise to this sum of a cosine term and a sine term at the same frequency. In fact, we already see the frequency, that's omega. To do that, let's go ahead and push the r through both. Let's reorient the two terms in the blue bracketed expression so that we now have r cosine theta weighting cosine omega t, and we have minus r sine theta weighting sine omega t. Or now r cosine theta. Cosine theta, theta is a fixed angle, cosine theta is a number, r is a number. Let's just collapse that into some coefficient alpha bar, and minus r sine theta, let's collapse that into some beta bar. e to the minus sigma t is the exponential damping, which is common to both terms. Meaning we can now rewrite that original f expression as a cosine with a phase shift as a linear combination of a sine and a cosine of the same frequency omega. They're both exponentially damped by an amount e to the minus sigma t. And if you now wanted to relate, if you had an expression that was in terms of the cosine and the sine, then, or I'm sorry, if you had an expression in terms of r and theta in this single cosine, you could find the alpha bar and the beta bar by simply computing r cosine theta, that's alpha bar, and minus r sine theta, that's beta bar. And then you would have this cosine and sine combination that's equivalent to the single cosine expression. Let's now say that you started with alpha bar and beta bar and you wanted to find the single cosine expression. Let's now just connect these alpha bars and beta bars with the r's and theta. And to do that, let's just look at alpha bar, square that, and square beta bar. That means we have r squared cosine squared of theta plus r squared sine squared of theta. And we know that the cosine squared plus sine squared is 1, which allows us now to say that alpha bar squared plus beta bar squared is r squared, or this combination of alpha bar and beta bar, if we take it alpha bar squared and beta bar squared and take the square root, that now gives us the magnitude of our single cosine expression. To find theta, let's now just take the ratio of beta bar to alpha bar, or minus r sine theta over r cosine theta. The r's cancel. Sine over cosine is just the tangent, and we now have beta bar over alpha bar as minus tangent of theta. We can take the inverse tangent of both sides, maybe after we've multiplied the numerator by minus 1, so that now we have a way of isolating the angle theta associated with the sine and cosine summation form of this f of t expression. So that now if somebody gave us alpha bar and beta bar in a exponentially damped structure of a sinusoid, if we now can identify alpha bar and beta bar, then we can actually put that into a single cosine with a phase shift formula by finding r as the square root of alpha bar squared plus beta bar squared, and the angle is the inverse tangent of minus beta bar over alpha bar. These four red boxes are then the connection between the sum of cosine sine and the single cosine expression. So in our particular example, where we had the exponentially damped cosine combined with the exponentially damped sine, now we can go into that. We can identify the omegas and the sigmas. The key, though, is finding the coefficients. Alpha bar is just 5, and beta bar is minus 8/3. R is now the square root of those two alpha bar and beta bar squared, which now ends up being 5.67, and that should look familiar. And the angle is now the inverse tangent of the negative of beta bar, which gives us then 8/3. So we now have the inverse tangent of 8 over 15, which 8 is less than 15, so we know that we're a little bit less than 45, and in fact we're at 28 degrees for our angle theta. So our f of t is now 5.67 e to the minus 2t cosine The exponential damping is the same. The frequency, the damped frequency is the same. It's just now we wanted to find the magnitude and the angle associated with that single cosine expression. We can also do this maybe a little bit more graphically by sketching a two-dimensional plane and plotting on that two-dimensional plane alpha bar and beta bar. With the alpha bar positive direction, the alpha bar is the coefficient of the cosine. We have that positive to the right. The sine coefficient is beta bar, and we actually have its positive direction going down. In our particular case, we had an alpha bar of 5, so we step over to the right 5 units. Our sine coefficient, S-I-N-E, had a negative sign, so we actually go up because that's the negative direction of the beta bar axis, and we go up minus 8/3 or minus 2 2/3 in the positive direction. That now will give us the horizontal and vertical dimensions of this rectangular box. The box now, we can create the diagonal of that box, and that's the amplitude of our single cosine. R is now just the hypotenuse of a right triangle with legs of 5 8/3, and the angle theta now is measured positively with respect to this cosine direction that's positive to the right, and it's positive in the counterclockwise direction. So now we have theta is going to be the inverse tangent of this distance of 8/3 divided by 5. And that's now this inverse tangent of 8/15. And that angle now becomes 28 degrees. So when we're computing this angle theta, make sure that you negate the negative sign on that minus 8/3. And if you're sort of trying to check your thinking or thought process, you could potentially remember or recall the sine of x is equal to the cosine of x minus 90. Then if you remember the cosine of two angles formula, cosine x, cosine minus 90, cosine minus 90 is 0, minus sine x, sine of minus 90, sine of minus 90 is minus 1, then you can double check your thinking and say, oh, if I plugged in 90 degrees, sine of 90 is 1. That should equal cosine of 90 minus 90, that's 0, that's 1. So there is a way of checking your memory on this expression, sine of x equal cosine of x minus 90. But if you want to quickly find the connection between the sum of sine and cosine, sometimes sketching this graph is quick for finding the amplitude of the cosine and its angle. Just remember that once you've plotted that dot in the vertical direction, theta will be measured positively going from the right horizontal axis in a counterclockwise direction. We can do it that way, or you can have these four boxed quantities relative to the expressions for f in terms of the sine and cosine, and f in terms of r and angle theta. And that should then convince you of this equivalence between the two expressions for exponentially damped sinusoids, and we now know how to compute using real number arithmetic the combination of exponentially damped cosine and exponentially damped sine for the inverse Laplace transform.